Today we're going to learn about finding inflection points of functions. Let's say we have to find the x-coordinates of the inflection points of f of x is equal to x to the fourth over 12 minus x cubed over 3 minus 15x squared over 2. So, how do we do this? Well, we know what inflection points are. Inflection points are where the concavity changes. So basically, it's where you have a negative concavity that changes to a positive concavity. Or you have a function that is concave down and then it changes to concave up. So let's first outline the steps that we need to do. So because we know that the inflection points deal with concavity, we'll have to figure out what type of derivative deals with concavity. So we also remember from our calculus class that the second derivative deals with concavity. So we know that we have to calculate the second derivative. Now what do we do once we know what the second derivative is? Well, that's simple. Once we know what the second derivative is, then we have to make a sign line and then calculate where the second derivative is positive and where it's negative, and after finding the roots of the second derivative, then we'll determine using the sign line which roots are inflection points. So, let's take a look at this problem here. So if this is f prime of x, that means that f of x, if this is f of x, then that means that f prime of x is equal to, let's write this higher, that means that f prime of x is equal to, so we use the power rule to take the first derivative, so x to the third power over 3, use the power rule again, x to the minus x to the second power over, or just x to the second power minus 15x. So, now that we have the first derivative, we can calculate the second derivative by taking the derivative of the first derivative. So that means that f double prime of x, or the second derivative of x, is equal to, or the second derivative of f of x, is equal to x squared minus 2x minus 15. So now what do we do? Well, now that we have the second derivative, to give ourselves more space, let's write it up here and erase the first derivative, because we don't need that anymore. So f double prime of x is equal to x squared minus 2x minus 15. So, now what do we do? Well, the first step after this is to calculate the roots of the second derivative. After we calculate the roots of the second derivative, then we can make a sign line and calculate where the inflection points are. So, the roots of this derivative are at, so as you can see, this is a trinomial, and it's a quadratic, so that means that it's the product of two binomials. So because this is a quadratic, we can factor this. So we know that it's positive x squared, so we have x in both of these. And because we know that this is negative, we know that it has to be plus something and minus something. Now let's calculate the factors of 15. They are 1 and 15, or it would have to be positive or negative 1 of 15. They would have to be plus or minus 1, plus or minus 15, plus or minus 3, and plus or minus 5. So we know that adding negative 1 to positive 15 or adding negative 15 to positive 1 wouldn't work, and we wouldn't be able to add, so that means that 15 is out of question. So now what could we do? Well, we know that if 15 is out of question, then that means that 1 is also out of question, because 1 multiplied by 3, or 5, is not equal to negative 15. So we have plus or minus 3 and plus or minus 5. Well, we know that this is negative 2 as the b. So that means that the bigger term has to be negative, because when they're added together you get a negative term. So that means that we have minus 5 and plus 3. And we also know that 3 plus negative 5 is negative 2. So this does work. So we have f double prime of x is equal to this. So now we can set this equal to 0 to find the roots. So we get that the roots are x is equal to negative 3 and positive 5. So now that we have the roots, we can erase this thing. We don't have to. So we have f double prime of x. So just to clear up some more room, before we clear up some more room actually, let's just make a sign line. So we have this side, and it comes here. And we know that this is the sign line of f double prime of x. And now we know that the two roots that we're looking at are negative 3 and 5. And notice that these are not evenly spaced out. It's not supposed to be like this. The spacing doesn't really matter with a sign line. You're just looking at the intervals between the numbers. And we know that this would continue to negative infinity and would continue to positive infinity. So now we have to list the factors. So looking at these two factors, or just this one factor, which one would be easier to use? So looking at two simpler factors would be easy, in this case, would be easier to use for our sign line than just looking at this one big function here. So let's erase f prime of this first one here, so we can use this more simpler version, which is just the factored down version. And let's move this up here. So f double prime of x is equal to x plus 3 times x minus 5. So we can erase this. And we know that the two roots are x is equal to negative 3 and positive 5. And so now let's put down the factors on the sign line. The first factor would be x plus 3. And the second factor would be x minus 5. So let's look at this sign line. So the first factor, x plus 3. From negative 3 to infinity, let's pick a number. So let's pick the number negative 4. That's on that interval. So if we pick the number negative 4 plus 3 is negative 1, which is a negative number. And we'll notice this is true for any number that we pick on the domain, on the closed domain, or the open domain, open interval, from negative 3 to negative infinity. Even if we go to negative 3.0001, that'll still be a negative number. It'll just be 0.0001. Now let's look at x minus 5. Let's pick the value negative 4 again. If we pick negative 4, then we get negative 4 minus 5, which is negative 9. We'll notice that this is still true for all the values on the interval from negative infinity to negative 3. If we pick negative 3.001, we get negative 3.001 minus 5 is negative 8.001. So this is negative. Now let's move on. From negative 3 to 5. If we pick a value, let's say we pick the value 0. 0 plus 3 is equal to 3, which is a positive number. We'll notice that this is true for any value on this open interval from negative 3 to 5. Let's say we picked negative 2.9. Negative 2.9 plus 3 would be 0.1. Now let's look at this other factor here, x minus 5. So if we pick a value, let's say again 0, and we do 0 minus 5, then we're still left with the negative number. So this would be negative up here. And we'll notice once again that this is true on any value on this open interval. And also one thing to notice is that negative 3 is the opposite of this value here, and 5 is the opposite of this value here. And so it would make sense if when you plugged in one of these two values into one of these functions, or one of these factors, one of them would turn out to be 0. If we plugged in a negative 3 into this factor, it would turn out to be 0. If we plugged in 5 into this factor, it would turn out to be 0. So that's why these intervals are like this, where they are true for the whole interval. So if we move on from 5 to infinity, we know that anything greater than 5 minus 5 will be positive, right? And anything greater than 5 plus 3 will also be positive. And this is true for anything greater than negative 3. Anything greater than negative 3 will be positive for this lower factor. And that's why it's positive on this interval here. However, anything that's less than 3, negative 3, plus 3 will have to be negative. Once again, that goes true for these two here. Anything that's less than 5 minus 5 will have to be negative. So that's why these two are both negative. So for this factor, it's negative on this domain and positive on this domain. So it's negative from negative infinity to 5 and positive from 5 to infinity. And for this lower factor here, x plus 3, it's negative from negative infinity to negative 3 and positive on the open interval from negative 3 to infinity. So you can see that it works out like that. Let's erase these marks. So now the last step is the simplest step. All we have to do is just multiply these signs. Because we know that these will be the signs of any number that we picked on that interval and when we plugged it in. So if we pick negative 4, then negative 4 minus 5 is negative 9, and negative 4 plus 3 is negative 1. Those both have the signs of negative, and when we multiply them together, because these are factors once again, it'll come out to be a positive number. So negative 9 times negative 1 would have to be positive 9. So we can just multiply these, or see what they would be if we did multiply them together. So positive and negative, we know when they're multiplied together, become negative. Negative and negative become positive, and positive become positive, or stay positive, I should say. You can't see that. So let's move this over. It would stay positive. So these are the two types of signs that you'll see, because they're the only two signs, positive and negative. And these are the only combinations that you'll see. Negative, negative, positive and negative in either way, and positive and positive. So now let's look at what we're dealing with. So we can see that the concavity changes from positive to negative back to positive. So if the concavity changes from positive to negative, or from negative to positive, so that means that it passes when it equals 0. So that means that there's an inflection point, because once again, an inflection point is where concavity changes from positive to negative, or negative to positive. It's when concavity changes from concave down to concave up. So this happens. Here it's concave up, and it changes to concave down. From here it's concave down, and it changes to concave up. So if these are the parts where it changes, then that means that x equals negative 3 and x equals 5 are the x-coordinates of the inflection points. So we can just say that here, that they are the x-coordinates of the inflection points. So this is the answer to this one problem. However, we are going to look at one exception to this. Not to this particular problem, but to where you just find the roots and all the roots are in the inflection points. So there are some times when all the roots are not the inflection points. Now that we're done with this, you can take a look at this, and then I'll go into what I mean. So let's just look at one example where not all the roots are the inflection points. This is just going to be one simple problem. Let's say that we had a graph. So if this is the graph, sorry, it's taking some time. And let's say that we had, let's say the second derivative looking like this. It comes down like that, goes up like that, like that. So let's say the second derivative would look like this. There would be an exception to having all the roots being inflection points. So we can see we have a single root here, a single root here, and then a double root here. So the place where there's a double root would not be an inflection point. Can you guys guess why? Well, this would be an inflection point because the concavity changes from positive to negative. This would be an inflection point where concavity changes from negative to positive. But this would not be an inflection point because the concavity is from positive to positive, so it stays the same. So one thing to remember is that whenever you have double roots or roots to the fourth power, or like that, or whenever you have a root that just touches the x-axis but does not pass through the x-axis or does not intersect it, it's just tangent to the x-axis, that's when you do not have an inflection point. So that's the key reason that you need to have a sign line. So you need the sign line so that you don't, from mistake, take this as an inflection point. Today we learned about finding inflection points of functions in calculus. Thank you for watching this video.